All right. So we left off talking about how we have Bernoulli's principle that the pressure based on different energies, so the work, the kinetic energy, and the gravitational potential energy, right? All translates into different pressures that we can add up. And if we have conservation of energy, we actually have the conservation of these types of pressures. Okay. We said that they could be held constant at that value. So what we have now is we have Torricelli's theorem. Torricelli's theorem is going to start off with the same thing, Bernoulli's equation. Now we have pressure, 1 plus 1/2, what is it, rho v squared plus rho gh. Can somebody glance back and double check that for me? And then equals the same thing, right? Plus 1/2 rho v squared plus rho gh.
Yeah, just make the velocity.
2, right? Velocity what?
Not volume. So
Yeah, arrow. And to make sure that it's not a volume, we have little arrows. And Torricelli said if we punch a hole in a side of a large tank, well, a couple of things we could factor out a couple of things, okay? So the first thing, the pressure at both parts is going to be atmospheric pressure, top and bottom. So at the top, there's atmospheric pressure above here. Right here, there's atmospheric pressure. Yeah, there's a slight height change, but atmospheric pressure doesn't change much for a couple of feet or even like 50 feet. And if your tank is bigger than 50 feet, you're going to have more issues with the pressure changed otherwise. So it's negligible. And then we have the speed at which the water is that it drains out is much lower than the speed of the water shooting out of the hole. So small hole means it shoots out far. Large tank means it goes down very slow, right? And so the speed is negligible. So let's just take a look at what that translates into. First off, why don't we worry about atmospheric pressure? If we're not worried about atmospheric pressure, what could we call the same? The latent pressure around the activity, right? So we just have no pressure around there. Not that we don't have pressure, they cancel out, right? It's all underneath the same atmosphere. And then what else? We have no speed based on the tank dropping its height, right? So this speed means that goes away, right? So pressure is both atmospheric pressure, and the speed doesn't really matter in terms of how much the tank is draining by. But we do have a height here, okay? Height 1 is the height of the tank. Height 2 is going to be this hole, okay? So that we have the density of the liquid, gravity times height equals 1/2 the density of the liquid and the speed that it's shooting out the hole squared.
Is it the middle of the hole, the bottom of the hole, or the top of the hole?
The hole will be small enough to where it's just the hole in general.
Okay.
Plus the density of the liquid times gravity times the height of where the hole is, right? And so what I'm starting to see is that all of these have what else? Rho. Okay, so if I have gravity times the change in height equals 1/2 velocity squared. Yeah, it's the speed that it shoots out, right? It's the only velocity that we're worried about. So if I'm trying to figure out how fast it's shooting out, if I'm trying to find out how fast it's shooting out, it's just the speed that it shoots out is equal to root 2g h. Oh, I feel like we've seen this formula before, but the cause of it shooting out is all the stacked height here that the liquid has to draw from. And it's pretty much saying it's the speed based on the top of the liquid here pushing down here. So it looks a lot like your kinematics formula. If we rearranged Vf squared equals Vi squared plus 2ax or 2gx, right? If we said the initial speed is 0, it's kind of getting its energy, and that's where that equation came from up here. And again, same source equations, we're talking about energy, and so the energy coming from the top of the liquid here is also shooting it out with its speed. Therefore, the equation actually looks pretty much the same. Speed equals to root 2g change in height.